If you've ever tried to simplify a really complex business problem, say predicting next quarter's sales revenue,
Right.
you realize pretty fast that looking at just one factor is, well, it's basically useless. If you only look at marketing spend, you're ignoring seasonality competitors.
Everything else, exactly. Simple linear regression is a great place to start. It's our analytical jumping off point for X on Y.
Yeah.
But it is fundamentally unrealistic for any complex system.
So to really model something like house prices or employee productivity, we have to go deeper.
We have to. We have to move into the world of multiple linear regression, or MLR.
And that is exactly our mission for this deep dive. We're going to jump into the source material on MLR and really try to understand its superpower.
Which is that ability to isolate all the unique contributions in that tangled web you mentioned.
Yes, and pull out the crucial rules, not just for interpretation, but for figuring out if the model we built is actually reliable enough to, make a business decision on.
Conceptually, it's a pretty intuitive leap.
Right.
You're moving from a single cause to multiple causes. So instead of just saying outcome Y is because of factor X, we say.
It's because of X1 plus X2 plus X3 and so on.
Exactly. You're just stacking your predictors to build a much more comprehensive and hopefully more accurate model.
So if that's the basic idea, what's the single most critical phrase, that analytical superpower that MLR gives us?
It all comes down to how you interpret the coefficients. In MLR, the meaning of a coefficient totally transforms. It's not just the relationship between that one X and Y anymore.
Okay.
It tells you the change in Y for a one-unit change in that specific X, but, and this is the critical part, you have to add the phrase, holding all other variables constant.
And that's everything. That is the foundation of evidence-based decision-making. You're basically creating a little laboratory inside your data.
That's a perfect way to put it. You're untangling the effects. If training hours and employee experience usually go up together, MLR lets you estimate the impact of just the training, assuming experience didn't change at all.
Okay, let's unpack the building blocks then, starting with the one part of the equation that often trips people up, the intercept, baseline.
The intercept, yeah. It's often labeled beta 0, and it's the theoretical predicted value of Y when every single one of your predictors is set to 0.
Theoretical being the key word there.
It really is. Mathematically, you need it to anchor the whole model, but practically, it's often completely meaningless.
Because it exists outside of reality.
Totally. Let's go back to a real estate price model. The intercept would be the predicted price of a house with, 0 square feet, 0 bedrooms, and 0 age.
A house that does not exist.
And will never exist. So we need it for the math to work, but we almost never try to get business insight from the intercept itself.
That makes a lot of sense. The real action, the engine of the model, is in those coefficients, the slopes. So let's bring in our classic example, the real estate price model.
Perfect. So let's say our model looks like this. Price equals 50 plus 0.12 times square feet plus 40 times bedrooms minus 2 times age.
Okay, let's break that down. The square footage one, beta 1, is 0.12. So a 1-unit change, one more square foot, increases the price by $0.12 thousand.
So $120.
$120 seems straightforward.
It is, as long as you use the full MLR interpretation. Each additional square foot adds $120 to the price.
Holding the number of bedrooms and the age of the house constant.
Exactly. That is the pure value of just physical space.
But this is where it gets really powerful. Look at the bedroom coefficient. Beta 2 is 40. Each extra bedroom adds $40,000 to the price.
Right.
But if square footage only accounts for the size, what is that $40,000 actually buying you?
And that is the critical business insight. That $40,000 premium, that's what buyers are paying for functionality, for separation, privacy, a dedicated space, all of that stuff beyond the raw square footage that room takes up.
Yeah. So MLR has actually isolated the value of bedroomness from the value of square footageness.
It's untangled them. With simple regression, you never know if the price went up just because a bedroom adds space or if there was a real premium on top of that. This model tells you there is.
And it works for negative effects too. The age coefficient, -2.
Our depreciation factor. For every year a house gets older, the price drops by $2,000. Again, holding its size and bedroom count constant. That's the unique cost of time, of wear and tear.
So we can use this to make a really specific prediction. Say we have a house, 1,600 square feet, 3 bedrooms, 12 years old.
Yep.
Plug it all in, and the model predicts a price of $338,000. That's a great starting point for an agent.
It is, but we have to pause here and address a really common mistake.
Which is?
Assuming the size of the coefficient means it's the most important variable. You see 40 for bedrooms and 0.12 for square footage, and you think bedrooms must be way more important.
But they're not, because the scales are completely different. $40,000 per bedroom versus $120 per square foot.
Precisely. To get the real business impact, you have to look at the realistic range of each variable. Our analysis showed that square footage, just because it varies so much, can swing the price by $240,000.
Bedrooms.
Only about $120,000. Age was even less, about an $80,000 swing.
So if you're advising a developer, you say, look, that 40 grand premium for a bedroom is great, but the biggest single driver of price variation in this market is overall square footage. That's where you focus.
It moves the conversation from just stats to actual strategy. That's the leap.
Speaking of leaps, let's move from interpreting to assessing. We've built this great model. How do we know if it's any good?
Right. Is it reliable?
And the first metric everyone jumps to is R squared.
R squared is our starting point. It's the proportion of variance in our outcome and the price that's explained by our predictors. So an R squared of 0.85 means our model explains 85% of why prices vary.
Which sounds great. A strong model.
It is a strong model. But the source material is very clear. R squared is deeply flawed, especially when you start comparing models.
Why?
Because R squared is a cheat. It's greedy. It will always go up when you add a new variable. Always.
Even if the variable is completely useless.
Even if this random noise. You could add the phase of the moon as a predictor, and your R squared would tick up just a tiny bit. It rewards complexity for complexity's sake.
So if we want to be responsible, we need a metric that penalizes R squared for adding useless stuff.
And that brings us to the hero of model comparison, adjusted R squared.
The keyword being adjusted.
Absolutely. Adjusted R squared introduces a penalty for complexity. It only goes up if the new variable you added explains more than enough variance to justify its own existence.
So the rule for everyone listening is simple. If you're comparing a model with 3 factors to one with 4, you have to look at adjusted R squared.
Always. Always use adjusted R squared when comparing models with different numbers of predictors. If you add a variable and your adjusted R squared goes down,
get rid of it. It's hurting more than it's helping.
It's just noise. This metric forces you to build simpler, more robust models.
Okay, so we know how much variance we've explained, but what about accuracy? How close are our predictions in, actual dollars and cents?
That's where the root mean square error, or RMSE, comes in. And it's fantastic because it quantifies your typical prediction error in the original units, in dollars in this case.
So back to our $338,000 prediction, if the RMSE is, say, $18,000, how does that change things?
It transforms it from a single guess into a useful range. An RMSE of $18,000 lets you tell your stakeholder that, yeah, the prediction is $338K, but there's a margin of error.
And as a rule of thumb, we can create a 95% prediction interval with that.
Yep, pretty good one. You just take the prediction plus or minus 2 times the RMSE.
So 338K plus or minus 36,000. That means the house is likely to sell somewhere between 302 and 374.
Precisely. And that's not a guess anymore. That's business intelligence. It manages expectations because it accounts for the model's uncertainty.
Which takes us right into our final crucial section, avoiding the common traps that can completely ruin an MLR model.
Because even a high adjusted R squared can be hiding some serious problems.
And the first one is when your predictors get a little too cozy with each other.
We call that multilinearity. It's when 2 or more of your predictors are highly correlated with each other. Say, a correlation above 0.7 or below negative 0.7.
It's like trying to figure out which of 2 employees gets credit for a project when they always work together.
That's the perfect analogy. You can't tell who is responsible for what. And in the model, it means the individual coefficients become violently unstable and unreliable.
So that core MLR insight holding other variables constant, it just breaks down.
It completely breaks down because you can't realistically hold one variable constant while the other one moves if they're basically tethered together in the data. Your interpretation is shot.
Meaning the model is useless for understanding the why.
Absolutely. The solution is usually to remove one of the correlated variables or maybe combine them. Now, I should say, if your only goal is pure prediction and you don't care about the why, you might get away with it, but your interpretations are gone.
Okay, trap number 2. This is the big one. Overfitting.
Ah, yes, the data equivalent of memorizing the test.
You build a model that fits your historical data perfectly. It captures every little hiccup and bit of noise, and then it completely fails on any new data.
The warning lights on this are very bright. You'll see a ridiculously high R-squared, like 0.98 or 0.99.
But a huge alarming gap between that and your adjusted R-square.
Exactly. That big drop is the model screaming at you that you've added so much complexity that it's just memorized noise, not learned a signal.
So how do we prevent that? Is there a rule of thumb for sample size?
There is. And it's a foundational rule beginners often ignore. The simplest explanation is usually the best one. That's Occam's razor. But for sample size, a good rule of thumb is you need at least 10 observations for every predictor variable you have, plus another 30 on top of that.
So for a model with 5 predictors, I need at least 80 data points. 10 times 5 plus 30, that's a pretty high bar.
It is, but it's a necessary one to stop you from measuring noise. Ultimately, the best way to prevent overfitting is to test your model on data it has never seen before, a holdout set.
And finally, a quick warning about pushing the model too far.
The extrapolation warning. Your model only understands the world based on the data you gave it. If your houses were all between 1 and 3,000 square feet, you can't use that model to predict the price of a 5,000 square foot mansion.
Because you're assuming that straight line relationship continues forever.
And it almost never does. Relationships curve, they break. Stick to predicting within the range your model was built on.
Okay, this has been an incredible deep dive. This is the toolkit for moving into realistic business modeling. Let's boil it down to the 3 key takeaways.
First, multiple linear regression is really the only practical way to analyze complex, real-world problems because it lets you control for multiple factors at the same time.
Second, the interpretation of every single MLR coefficient lives and dies by one phrase, holding other variables constant. That is how you find those unique, actionable insights.
And third, you have to assess your model responsibly. Use adjusted R-squared to fight complexity and RMSE to understand your prediction accuracy in real-world units.
So we've covered how to build the model, interpret the coefficients, and check if it's any good.
But here is the final provocative thought I want to leave you with.
Okay.
We know our model says an extra bedroom adds $40,000 in price, but we don't know for sure if that $40,000 effect is real or if it's just a random fluke in our specific data sample.
So whether it's statistically significant.
Exactly. To do truly professional analysis, you have to know that. So the big question is, if you check your stats, your p-values, and find out that your $40,000 per bedroom coefficient is statistically unreliable, meaning the real value could actually be 0.
Wow.
What advice do you give your business stakeholder then? That's the next level of mastering the data.